This is notes from Chapter 5, Investment Problems. So mainly compound interest is what the gist of this section is. Alright, so this is our compound interest problem, okay? P is the original amount invested, and then K is how many times we compound the interest per year. Alright, T is the number of years the investment goes on. Okay, so this formula is one we're going to use a lot in this section. Alright, so to give you an example of how this formula is used, write an equation that gives the future value of $1,000 invested for T years at 8% compounded annually. Okay, now they want us to use S for the future value for whatever reason in this book, in this chapter. So that would be S equals 1,000. If you look at the formula, P is the dollars that are invested. So here the $1,000 is what's invested, so that'll be S equals $1,000 parentheses, and then we have this 1 plus and then the fraction. So 1 plus, and then the R over K, R is the percent interest rate given as a decimal, so 0.08 divided by K is the number of compound periods in a year. Right, annually means K is equal to 1 period per year, so 1 goes there. Alright, and then in parentheses, or in the parentheses, and then you have K times T as your exponent. Okay, so T is our exponent. T years times K equals 1, so 1 times K up here. Alright, there's our formula, or just simplifying a little bit because of the division multiplication by 1, we'd end up with S equals 1,000 times 1.08 to the T power. Okay, when it's dividing by 1, 0.08 divided by 1 is 0.08, and then 1 plus 0.08 is 1.08, and then 1 times K, sorry, that should have been a T there. 1 times T is just T. So there's where that T is coming from. Alright, now B says write the equation that gives the future value of $1,000 invested for T years at 8% interest compounded daily, right, instead of annually. So here K is equal to 365 because there's 365 days in a year. So the difference here is it looks like S equals 1,000 times 1 plus 0.08 divided by 365, right, to the K times T, 365 times T, right. And here actually nothing I can really do with that, because this fraction, if I were to actually divide it, 0.08 divided by 365 is a really ugly decimal that we wouldn't use to approximate that. Okay, it keeps on going, has a pattern, but it's not visible for a while, so we would just leave it like this. Okay, that's another really important thing about this, is you got to make sure that you are leaving these exact with like this form for as long as you can. You'll notice that in your homework, if you try to simplify and round, a lot of times, approximate and round, a lot of times you'll get an error message when you get to your final answer. Alright, C wants us to graph the equations on the same axis, both of these two equations on the same axis. Alright, so this is what it's going to look like, and I do just want to show you that it really does look like that. If I put these in my calculator, I'll notice here, if you're following along with the previous homework, if you have your plot 1 on, make sure you turn that off. Alright, now I'm going to put these equations in my calculator. Alright, this is what they look like when they go into the calculator. 1,000, this is this one right here. 1.08 to the x power, 1,000, 1.08 divided by 365 to the 365 x power. A couple things to notice. One, it says t here in both of these equations, and I'm using x. Right, that doesn't matter, t, x, whatever you want to call it, but your calculator has x, so you'll use an x when you put in your calculator. And the other thing is this parentheses. When I have multiplication in the exponent, I've got to have, see, this is 365 times t. I've got to have multiplication, parentheses around multiplication in the exponent. So this is a really big error that a lot of people make sometimes. Alright, and now if I make the same window they have here from 0 to 30 and 0 to 10,000 for my window, so x is going to go from 0 to 30. Alright, x scale, let's make it 5. Alright, that went in 5s. Alright, and then y scale goes from 0 to 10,000. Oops, 0 to 10,000. 10,000. Alright, and then they put their scale in 2,000s. And if I graph that, here comes the first one, the 1,000 times 1.08 to the t, and then here comes the second one. Again, we can't see any separation until about halfway through, and then it goes a little bit higher. Okay, so this is virtually exactly what this graph that I have, and I just wanted to show you that you can regenerate that with your calculator. Just make sure you put this scale on there to make it look like this. Alright, then part D says, what's the additional amount of interest earned in 30 years from compounding daily rather than annually? Well, to do that, let's go to this graph that we have in here, and let's press trace, and let's get the two values at 30. So if I type in 30, hit enter. Alright, this is the bottom one. So 1062.657. Alright, that's in this one. So, I'm sorry, 10,062.657. 10,062.657. Alright, that's the lower one. That's what we're going to subtract. The other one's a little higher. Okay. Now to get that one, I had to press down. Alright, go to the other one, press trace, and press 30. Alright, and there's 10,000. Oops, that's in Y1. 11,020.278. Alright, if I do that subtraction, I get 11,020.278 minus 10,062.657. I get $957.62, so $957.62. Alright, so over the course of 30 years, it makes a pretty significant difference here. Now, another way you could do this rather quickly on your calculator, rather than doing it the way we did it, if you press the vars button and go over here to y vars like you do when we did the regression in the last section, and then y2 is where we have this function. So go to y2 and press parentheses 30, right, meaning we're putting 30 into the y2 function, and subtract, do it again, vars, y vars function, y1 this time, and put in 30. Alright, y1 is where we have this function. Okay, so we're putting in 30 into that function and putting 30 into this function. Alright, and there it goes to the cuts to the chase a little quicker. Alright, and then one other way you could have done it to get these two numbers is just press second table set. Alright, tell your table to start at 30. Hit enter, and then go to the table. Alright, and then there's the two numbers. Alright, and then you could get your decimals as many as you want. So there's the 11,020.27. I did 8, I rounded to 3 places. And then 10,062.657. Alright, So you could get it from there as well, all right, from the table. But any of those will give you a good approximation of what that is. This one's going to do all the work for you, though, if you get yourself comfortable with doing that. So just kind of rewatch the video a few times to get yourself comfortable with putting in a function and finding using that vars menu to find the difference between two outputs. Alright, continuous compounding. So continuous compounding, instead of compounding every day 365 times, or every hour, or every minute, or every second, continuous compounding virtually means we're always compounding interest. And if you see continuous compounding, you got to remember to use this formula instead of coming up with some value for k, right, from this formula. Okay, if k is equal, virtually if k is infinity, meaning we're doing it all the time, an infinite amount of times, then we come up with this formula instead. Alright, so let's just show you how it works. Part A. What's the future value of $26.50 invested for 8 years at 12% compounded continuously? So S equals P stands for the dollars that were invested, so that's $26.50. Alright, and then E to the 8 years is T, 0.12 is R. So E to the 0.12 times T was 8 power. Now, when you do this, first of all, here is the E to the X button. It's right above ln, E to the X power. You write in the first number, 2650, and then you just go ahead and press second, ln. Alright, and there's the E to the power of, E to the power of. But don't forget this. Alright, again, you have multiplication in there. It already puts the parentheses around it just because it's such a common error. But we need the 0.12 to be multiplied by 8. Alright, we get 6921 virtually. Alright, now how much interest will be earned on the investment for part B? Remember, this tells you how much is in there. The interest is what we started with, take away from what we ended up with. So interest equals the 6921 minus the 2650. Alright, this is the last thing I did, so just minus 2650. Alright, and I roughly get 4271. Alright, and that's money, so dollars. Alright, now this is just some examples from your homework just to kind of get used to using these formulas that you'll see in this section. So question 5, this is something from your homework. What lump sum must be invested at 11% compounded monthly for the investment to grow to $72,000? Alright, so this is the formula for this is after the T years goes by. What a question like number 5 is asking is, what is it going to be, what do I have to put in now for it to be this amount in so many years? So let's think about this for a second. If S equals P times 1 plus R over K to the KT, then it follows that P is equal to S divided by all that stuff. 1 plus R over K to the KT. Alright, does everybody see why? If not, just look, this is what I've got isolated over here. So to get it isolated, what do I have to do? I have to divide by all this stuff up above it. And if I do that to the left, to keep this equal sign true, I have to do it to the right. Alright, so this cancels over here, and that's where this formula is coming from. Now, another way to do this formula is, what I like to do is, instead of division, I like to keep it with multiplication, but to make this a negative exponent. KT. Remember, negative exponents. A negative exponent being multiplied by something sends it down to the bottom and makes it a positive exponent. So these two things are equivalent. I like this one better just because it keeps everything with multiplication rather than division. Alright, so for this one, what lump sum, that's the P that we're looking for, must be invested at 11%, that's R, compounded monthly, so that means K equals 12, for the investment to grow to 72,000, so that's S, in 14 years, and there's T. So we've got everything we need to plug in. P equals 72,000 parentheses 1 plus R is 0.11 over K is 12 raised to the negative 12 times T is 14, so negative 12 times 14. Alright, and again I'm going to go to the calculator, type in exactly what I have there. Alright, so there's this 72,000 times 1 plus 0.11 divided by 12 raised to the, don't forget your parentheses, 12 times 14, and don't forget the negative like I just did. Insert, if you leave it off a second, insert will let you stick it back in there. Alright, and then enter. So that means we have to put in $15,544 and 11 cents. $544, and don't forget those 11 cents because they make all the difference. Alright, this is what I have to put in there to get $72,000 after 14 years. Alright, this over here is what you need. This is the present value or the lump sum formula. Alright, and at the end of T years, the future value of an investment of $12,000 on an account pays 12% APR compounded monthly is that. Alright, assuming no withdrawals or additional deposits, how long will it take for it to reach $48,000? Now, a couple ways you can do this. One, you can do it out by hand. We're just using the same old formula we've been using. S equals P times 1 plus R over K to the KT. Alright, so S, we're told that this is S. This is what we're going to grow to. This is P. Okay, so 48,000 equals 12,000 times 12,000 times 1 plus R was 12%. Alright, and write that as a decimal, so 0.12 over K, which is monthly, so K is 12 again. Alright, raised to the 12, which is K again, times T. T is what we don't know here. Alright, this is what we're solving for in this problem. Alright, we know S, we know P, we know R, we know K. T is the only thing we don't know. Alright, now, the way we're supposed to do this problem is isolate this exponential part. So we want to isolate the exponential, meaning we want to get this part over here by itself. Oops. This part by itself. So the first thing we're going to do is divide away the 12,000. So that's gone, that's gone. So 48,000 divided by 12,000 is 4. And then 4 equals 1 plus 0.12 divided by 12 is 0.01. Alright. So that's where this is coming from. I'm just taking the numerator, dividing by the denominator, and I'm getting that. So that's where this 0.01 is coming from. I'm just doing this division. Alright, to the 12t, and then just simplifying a little bit. This is 1.01 to the 12t. Now, we're supposed to use properties of logs and all those things we've studied in the last chapter, meaning we're going to bring in natural logs into this thing. So two things are equal. The natural logs of those two things are also going to be equal. Alright, and then the idea here is I can bring down that exponent. That's one of the properties of logs that we talked about in another chapter. And that brings this 12t down. Alright, and now we divide away the 12 natural log of 1.01 to both sides, and who's isolated. Well, 12 cancels, natural log of 1.01 cancels, and we're left with t is equal to exactly the natural log of 4 divided by 12 times the natural log of 1.01. Okay, that's the exact answer. But, you know, if somebody asks you how old you were and you said, I'm the natural log of 4 divided by 12 times the natural log of 1.01, they would just look at you and say, alright, well, how old are you? Alright, so the point is approximate it. Give me a good approximation for this. Alright, so go to your calculator, clear it out. Natural log of 4 divided by, we got multiplication down there in denominator, so we need parentheses. 12 times the natural log of 1.01. Alright, so approximately 11.61 years. Alright, now, a way that if you had no idea how to do this, remember, any equation, if you can set this up, and you should definitely be able to set this up, any equation that you set up can be solved by putting the left side of the equation in y1, the right side of the equation in y2. Alright, I've got, there's the left side, the 48,000. There's the right side, 12,001 plus 0.12 divided by 12 to the parentheses. Don't forget the parentheses. 12x. Okay, I've got this window, 0 to 30, x scale of 5, 0 to 50,000. Alright, x scale of 5,000. Alright, 50,000 because we've got to be above 48,000. And then if I hit graph, there's the 48,000. And here comes our function. Alright, and then there's where they cross. And I'm just looking for that intersection. So option 5, first curve, that one, second curve, that one, and then the guess. Just try to get it close. It's hard to see it here. Alright, there's my curve, so I hit enter. And there's our guess. 11.61, 48,000. 11.61 is what we got here. So remember, you can always use this. Always use this if you get stuck and don't know how to do it exactly. Any equation, left side y1, right side y2, graph it, move the window around until you see the intersection, and then find the intersection with option 5.